Good morning, class. We will now begin Chapter 8. We will start by looking at Section 8.1, Estimating Population Means when sigma is known. Now remember, sigma is our population standard deviation. So one of the key concepts in statistical analysis is that of estimating population parameters. Researchers and statisticians estimate a wide variety of parameters, anything from the average price of a flight to Europe to the proportion of voters who favor one candidate over another. The major purpose of statistics is to provide information so that informed decisions can be made. Recall that inferential statistics from Chapter 1 is the branch that uses sample statistics to provide estimates for population parameters. For a particular parameter, there may be a variety of sample statistics that could be used to provide estimates. When the estimate for a population is a single value, it is called a point estimate. Now recall that we can calculate the population mean as follows, and this was from Chapter 3. Mu is the sum of all our data points from our population, and capital N is the size of our population. However, this would require data from the entire population, which we usually do not have. Instead, let's consider trying to estimate the population mean mu. Three obvious statistics that could be used to estimate the population mean are the mean, median, and mode of a sample. And we saw all of these in Chapter 3. Now, it is not necessarily true of sample medians or sample modes that their values will be centered about the mean of the population. However, we know from our discussion of the central limit theorem that the mean of a sampling distribution of sample means is equal to the mean of the population. Therefore, we can say that the sample mean does not consistently underestimate or overestimate the population mean, and is actually the best point estimate of the population mean. So if we want to estimate the population mean with a single statistic, a single numeric value from the sample, we would use X bar, which is our sample mean. Let's look at an example. Find the best point estimate for the population mean of test scores on a standardized biology final exam. The following is a simple random sample taken from the population of test scores. Now notice there are 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5. There are 30 sample test scores here, right? And what we want to do is we want to find the best point estimate. And we just said the best point estimate for the population mean, the average of the population, is our sample mean, the average of our sample. So from Chapter 3, we know that X bar is the sum of all of our data points divided by the total number of sampled data values. And we get 81.6 in this case. Now, as you might imagine, using only one value for estimating the population mean or any other population parameter leaves much room for error. In fact, we have no way of knowing the likelihood that we have chosen the exact value of the parameter, or that we are even close to it, right? So if you think about it, this should make sense. Choosing a single number to estimate an entire population is probably not a good idea. So instead, we provide a range of values rather than just one number to estimate the parameter. This is what we call an interval estimate. For example, in our last example, we might estimate that the population mean for a standardized exam is between 75 and 85. So remember that our point estimate was 81.6, but now if we expand that to a range of values and look at all numbers between 75 and 85, we're more likely to have the true population mean in that range of values. We need to realize, however, that an interval estimate is still just an estimate. Just as we couldn't be certain that the point estimate was accurate, we also cannot be certain that the interval estimate contains the true value of our population mean mu. To account for this, we will use statistical methods to form an interval estimate for which there is a specified level of confidence. For example, if there is a 90% level of confidence given, what we can say is that we are confident that using this statistical method will result in 90% of all possible interval estimates containing the true value of our population mean mu. A visual representation for this is if we had 10 interval estimates. So we're getting each interval estimate from a different sampling. So we have 10 different samplings, and we look at our sample mean for each sample, and we expand that around the sample mean to create an interval estimate. So here's one interval estimate, here's another interval estimate, a third, a fourth, a fifth, a sixth, a seventh, eighth, ninth, and 10th. If we are 90% confident, then that tells us that in the long run, 9 out of 10 intervals will contain mu. So here's mu. Notice that each of these intervals contains mu. The only one that doesn't contain mu is this one, right? So we're going to use this idea of confidence. So let's recap. A point estimate is a single number estimate of a population parameter. An interval estimate is a range of possible values for a population parameter. The level of confidence we will denote by C, C for confidence, is the percentage of all possible samples of a given size that will produce interval estimates that contain the actual value of the parameter. And finally, a confidence interval, this is what we want to focus on in chapters 8 and 9. A confidence interval is an interval estimate associated with a certain level of confidence. Now, for the remainder of this section, we will discuss the technique for how we can create a confidence interval for our population mean with a given level of confidence. Obviously, the confidence interval should be constructed around the best point estimate we can find, which in this case would be the sample mean, x bar. But how do we make the interval? The largest possible distance away from the point estimate that the confidence interval will cover is called the margin of error, or maximum error of estimate. And we will denote this value by E, E for error. So, to construct confidence intervals for the population mean, mu, simply subtract the value E from the point estimate, x bar, and add the value E to the point estimate, x bar, as shown below. So we're going to find the point estimate. We know the point estimate is x bar. And to create our interval range, our interval estimate, we're going to subtract an error, and we're going to add an error to create a range of values that we call a confidence interval. Let's look at an example. A college student researching study habits collects data from a random sample of 250 college students on her campus and calculates that the sample mean is x bar equals 15.7 hours per week. If the margin of error for her data using a 95% level of confidence is error equals 0.6 hours, construct a 95% confidence interval for her data. We also want to interpret the results. So the interval will be centered around her sample mean, which we know from the problem is 15.7. Now, to find the lower endpoint of the confidence interval, we subtract the error. So we take x bar minus E which gives us 15.1. To find the upper endpoint of the confidence interval, we add the error. So we take x bar plus e, and we get 16.3. Note, from a basic algebra class, we will always write our confidence intervals as open intervals along the real number line. Remember that an open interval from A to B, where A is less than B, are real numbers, consists of all real numbers x such that x is between A and B. And we denote this as follows. So we have our number line, and we find the value A, and we find the value B on the number line, and the open interval, A to B, consists of all numbers between A and B. And we denote it as follows. The open interval, so we use open parentheses, A, comma, B. Using our notation, our confidence interval is, remember our lower endpoint was 15.1 and our upper endpoint was 16.3. So this is our open interval from 15.1 to 16.3. This tells us that we estimate our population mean mu as a number between 15.1 and 16.3. So that is mu is some number between 15.1 and 16.3. Now, if we want to interpret this result, we can say that we are 95% confident that the true population mean value for the number of hours per week that students on this campus spend studying is between 15.1 and 16.3 hours. Now, in the previous example, the margin of error was given to us, which was very nice. We will now see how to calculate the margin of error for our population mean when sigma is known. So we're going to start with the case where sigma is known. And if you look at your exam 4 formula sheet, we have all of our maximum error estimates listed, our values of E. Note, in general, if we are estimating the parameter mu, then it would seem silly to think that we would know the value of sigma. And think about why this is. Look back at chapter 3 at our formula for sigma. Notice that our formula for sigma uses the value mu. So if we know sigma, we can find mu. However, this scenario allows us to use our standard normal distribution, our z distribution, which we used in chapters 6 and 7, to help us calculate the value of our error, E. So the idea, the measure of how confident we are that the interval contains the mean mu, is the level of confidence C. This value corresponds to the area under the normal curve centered at the estimate for the population mean x bar. This is the area corresponding to the middle C%. The z values that mark the boundaries for the area of C under the middle of the standard normal curve are called critical z values and are denoted by negative z alpha over 2 and z alpha over 2. Notice that these values only differ by a sign because of the symmetry, right? So these are the same value except this one is negative and this one is positive. Now, the notation here, if the area under the middle of the curve equals C, then the area left over in the two tails equals 1 minus C. So using the complement rule, this was from chapter 4. We call this value alpha, and this is our lowercase Greek letter alpha. That is, alpha is the complement of our confidence, so it's 1 minus our confidence. By symmetry of the normal curve, the area in each tail is equal. So it must be the case that the area in each of the tails is alpha over 2. The value negative z alpha over 2 marks the boundary at which an area of alpha over 2 lies in the left tail of the curve. Similarly, the value z alpha over 2 marks the boundary at which the area of alpha over 2 lies in the right tail of the curve. The bottom of our statistical table, table B, displays commonly used critical z values for easy reference. Notice that they list our confidence level. We also have our alpha. This is our leftover area in the tails, which is our complement, and we have our critical z values. Now notice that the critical z values are always listed as our positive z alpha over 2. We won't need to worry about this for chapters 8 and 9, but when we get to chapters 10 and 11, we will need to worry about this. So just remember that it only gives the positive critical value. Now this is what we were saying. Notice that because of symmetry, we go the same distance to the right and left. The right value is z alpha over 2. Z alpha over 2 marks the boundary at which the area in the right tail is alpha over 2. And then if we go to the left, negative z alpha over 2, this marks the boundary value at which the area in the left tail is alpha over 2. And our confidence is the area in the middle. This shaded area gives us our confidence. Now a fact, the formula for the margin of error of a confidence interval for a population mean, mu, when the population standard deviation sigma is known, is the error is our critical z value times our standard deviation for our sampling distribution of sample means. Now, if we remember from chapter 7, our standard deviation for our sampling distribution of sample means is sigma over root n, where sigma is the standard deviation of our population distribution here. So our error is our critical z value, our positive boundary value, times sigma divided by the square root of n. And we are allowed to use sigma here because in these problems we're assuming that sigma is known. Notice that in this formula, again, let's remind ourselves, we use the positive critical z value corresponding to the area of alpha over 2 to the right. Let's look at an example. Researchers want to estimate the mean monthly electricity bill in a large urban area using a simple random sample of 100 households. Assume that the population standard deviation is known to be $15.50. Find the margin of error for a 99% confidence interval. So we're going to use this formula. So we need three things. We need our sample size, n, we need our population standard deviation, sigma, and we need to use table B or other techniques to find our critical z value. So here we notice that our simple random sample is 100. So this is our n. And notice that they tell us assume the population standard deviation. This is our sigma. Our sigma is $15.50. Now, the only thing we now need to find is our critical z value, right? We have sigma and we have n. To find our critical z value, we will use our confidence level, okay? So just a recap. From the problem, we know that n is 100. We know that sigma is 15.50. And our confidence is 99%. Now remember, whenever we use percentages in our calculations, we convert them to decimal values, okay? Don't forget that. So we will use our value C, which is 0.99, representing the 99% confidence, to find our critical z value, okay? So finding the z value using methods from section 6.4, okay? So let's recall from 6.4, we talked about the inverse normal distribution. So we know C is 0.99. So our alpha, this is our leftover area in our left tail and our area in our right tail. So alpha is the complement. So 1 minus 0.99 gives us 0.01. Therefore, alpha over 2, right? So we want to split it. Because it's symmetric, 0.01 is in both tails, and using symmetry, half of it is in each tail. So each tail, the left tail and the right tail, contains 0.005 of the area. So we want to find a z-value that corresponds to an area of 0.005 to the right of z. Remember, we're using the positive, so we're always talking about area to the right, okay? This means that 1 minus 0.005, which gives us 0.995, is to the left, right? Because our table, remember that tables A and B only give us values for areas to the left, okay? So this is equivalent to 0.9950, and I'm going to tack on that extra 0 because in my table, I always have 4 decimals, so I want to mimic my 4 decimals here. Okay, so to find our critical z-value, denoted by z alpha over 2, or we know that alpha over 2 is 0.005, we look for the area 0.9950 in table B. We see that the values z equals 2.57 and z equals 2.58 give areas of 0.9949 and 0.9951, which are the same distance from 0.9950. So to find our z-value, we take the average. And again, we're using techniques from 6.4 here. So taking the average, we get 2.575. And this is portrayed here in the next slide. So what we're doing is we're using our table B, and we're finding 0.9950. Now notice, I see 0.9949 and 0.9951. Between this is our value 0.9950, but it's not listed. So now we have to ask ourselves, which value is closer? Remember that we always use the closer distance value. But notice they're the same distance. So what we do is we follow this back. If we look at 0.9949, we get 2.57. Right? So z equals 2.57 corresponds to this area. And if we follow this back, we get 2.58. So z equals 2.58 corresponds to this area to the left. Now, since they're the same distance, section 6.4 told us to average those z values. So 2.57 plus 2.58 divided by 2, we average them, so we divide by 2, we get 2.575. Now, an easier technique, most of the time our confidence percentages are going to be listed in our table B. So finding z using our table of common values, this is the table found at the bottom of our table B. We look at the bottom of table B with c equals 0.99. Notice our level of confidence was 0.99, and we easily see that z equals 2.575. So any quiz or exam, this is going to be the case. I'm going to give you a value that's listed here. Every now and then, because the Hawks homework randomly generates numbers in the homework, sometimes you'll have to go back to our previous method, our 6.4 method, to find our critical value, our boundary value that blocks off the area to the right. Okay, so just remember that. But any quiz or exam, I'm going to set it up to where we can easily find it in our chart in the bottom of table B. Okay, so with that, we now calculate our margin of error. So we just said that our critical value was 2.575. Remember that our sigma was 15.50 and our n was 100. Multiplying these values together, we get 3.991250. So putting it all together. So how do we construct a confidence interval? Our first step, we use our confidence level to find our critical z-value. And this is, again, most of the times from the chart at the bottom of table B. Step 2, we want to calculate our margin of error. So we have our critical z-value. Now we need to reread the problem and we need to find our population standard deviation sigma and our sample size n. And then finally, step 3, we find the upper and lower endpoints of your interval by adding e to and subtracting e from our value x bar. So remember the idea at the beginning here. We're going to center the interval around our best point estimate. This is x bar. And we're going to then subtract e, and we're going to then add e to get our interval range, our interval estimate. And this is what we call our confidence interval. Okay, so let's look at an example putting it all together. To estimate the number of calls to expect at a new mental health hotline, volunteers contact a random sample of 35 similar hotlines across the nation and find that the sample mean is 42.0 calls per month. Construct a 95% confidence interval for the mean number of calls per month. Assume that the population standard deviation is known to be 6.5 calls per month. Okay, so just looking at this problem, we can automatically pull out a few things. Notice we have our random sample of 35. This is our n. We also are given that our sample mean is 42.0. This is our x bar. We also are wanting to find a 95% confidence interval. So this tells us that our confidence, C, is 0.95. And finally, we're assuming the population standard deviation, this is sigma, is 6.5. Okay, so we can pull out a lot of information right away and label it. It's very important that you not only read the problem and pull out the numeric values, but you correctly label the numeric values, because there's going to be a lot of formulas in chapters 8 and 9, and the labeling will help us see which formula we will use. Okay, so again, n is 35, this is our sample size. X bar, this is our sample mean, was 42.0. C, which is our confidence, was 0.95, and sigma, our population standard deviation, is 6.5. Now looking at the bottom of table B with 95% confidence, we see that Z is 1.96. Now, again, this is really our Z alpha over 2, but I'm going to ignore that silly notation because it's just a Z value, right? So I'm just going to call it Z. So my Z, my boundary value, is 1.96. So plugging this into our formula, Z times sigma over the square root of n, we get 2.15343. Okay, so this is our error. Now, to finish the problem, all we need to do is find our upper endpoint and lower endpoint of the interval. Our upper endpoint, we take our point estimate, remember our x bar, which was given to be 42.0, and we add our error that we just calculated. We get approximately 44.2. Our lower endpoint, we take our point estimate, our error, our sample mean, 42.0, and we subtract our error, and we get approximately 39.8. Okay, so our interval is written as 39.8 to 44.2. That is, we are 95% confident that the true population mean mu for the numbers of calls to mental health hotlines across the nation is between 39.8 and 44.2 calls per month. Now let's look at another example. However, this time we will utilize our graphing calculator. Or if you don't have a graphing calculator, we have access to our smartphone app. Okay, So a large greenhouse production wants to estimate the average number of days it takes for hydrangea seed to germinate. For a randomly selected sample of 125 seeds, the sample mean is found to be 13.9 days, assuming a standard deviation of 1.4, create a 90% confidence interval for the average number of days it takes for all hydrangea seeds to germinate. So now pause the video for a second and try to pull out and correctly label all of the numeric values. Okay? Now, what we will see here is that our N is 125, our X bar is 13.9, and our sigma is 1.4. And then finally, our confidence, C, is 0.90, okay? But this time what we want to do is we want to utilize our graphing calculator or our smartphone app. Now again, you can decide which method you use on the quizzes, homework quizzes, and exam, but I want to portray both for those that are interested in utilizing their calculator. So what we do is we first press our stat button on our graphing calculator. So remember that our stat button is here. Okay. Next, we highlight test and select z-interval. So we've been used to using our edit and our calc feature here, right, to calculate our 1var stats. But now what we want to do is we want to highlight our test, and we're going to look at our z-interval, right? We call it a z-interval because we're using a z critical value. So we're going to click on z-interval here. So next, we highlight stats. So we want to input our stats. Now, if you have raw data, you can input your data into your edit feature and list your data in column L1, and then you can highlight data. But in this case, they give us statistics, single numeric values. So we're going to highlight our stats, and we're going to plug in everything that we found and labeled. Remember that sigma was 1.4. Our mean, X, this is our X bar, was 13.9. Our N was 125. And our confidence level was 0.90. And now what we're going to do is hit enter. Okay, so we hit enter and we see our confidence interval. We get approximately 13.7 to approximately 14.1. So we are 90% confident that, what were we asked here? We wanted a confidence interval for the number of days it takes. So we're 90% confident that the true average number of days it takes, our mu, for hydrangea seeds to germinate is between 13.7 and 14.1 days. If we want to estimate our error, now notice, in this problem, now on the quizzes and the exam, I will ask you to find the error. Now you can just go back and use your calculator to calculate the error using our formula from the exam 4 formula sheet. However, if you utilize your calculator in this method, we can find the error using a trick. And we have to be a little clever here. So if we want to estimate our error, we can take the upper endpoint minus our sample mean, X bar. So I'm going to first take the upper endpoint. The upper endpoint is this 14.105968. And I'm going to subtract my sample mean. My sample mean in the problem was 13.9, and I get 0.205968. And this is my estimated error. So I can do that without using the formula, and that's okay. Now, suppose that you are a researcher and you want to conduct a statistical study with a high level of confidence and a reasonably small margin of error. It would be nice to have a very large sample with thousands of data values, but time and money prevent you from such luxuries. So a logical question at this point might be, how large of a sample do I need to obtain the desired level of confidence with a particular margin of error? We can calculate the minimum sample size necessary using the formula. So remember that error was given by this formula, our critical z-value times sigma divided by the square root of n. If we solve using algebra, doing some basic algebra, resolve this equation, right? This is equality. For n, we get n equals z times sigma over e squared. And a fun little exercise to remind you a little bit of how algebra works. Try to do this. Very, very easy. Now, if you're struggling, again, please reach out to me via our discussion board in Canvas or email. Let's look at an example using this formula. Now, again, this formula is on our exam 4 formula sheet, so you don't have to remember how to resolve this to get this. This is given to us. Determine the minimum sample size needed if we wish to be 90% confident that the sample mean is within 2 units of the population mean. An estimate for the population standard deviation of 8.4 is available from a previous study. Okay? So we know the following values from what is given in the problem, right? C is 90%, our confidence, and our sigma is approximately 8.4, right? We want a 90% confidence, and an estimate of the population standard deviation was given to us. This is our sigma. The phrase within 2 units in this problem indicates that the desired maximum margin of error is 2. So that is E equals 2. Using the bottom of table B, we see that Z alpha over 2 is 1.645. And again, please check this and verify that you're doing this correctly. And plugging everything into our formula, we have our Z, our sigma, our E. We calculate it and we get 47.734281. Now, since it's a sample size, it's dealing with whole number values, what we're going to do is we always, no matter what this decimal number is, we always round up. So we're going to use a sample size of 48. So again, just to reemphasize this, note that we always round up to the next larger whole number when computing the minimum sample size. If you have any questions, please email me or post in our discussion board.